Have you ever just looked up at the night sky and felt, well, a mix of total wonder and maybe a little bit of frustration? I mean, the universe is just so unbelievably vast. And that vastness makes traveling to other stars, let alone other galaxies, feel completely impossible. But what if there was a shortcut? Today, we are diving deep into the real science behind one of science fiction's absolute favorite ideas, the wormhole.
All right, so to really get our heads around this, we first have to understand the scale of the problem we're trying to solve. We live in the Milky Way, right? And our closest major galactic neighbor is Andromeda. It looks like this beautiful, faint smudge through a telescope. But actually getting there is, well, it's a bit of a trip, to put it mildly.
94.5 billion years. Just let that number sink in. That's almost 7 times the current age of the entire universe. So what on earth is this number? Yeah, that's how long it would take our fastest probe, which is screaming through space, to cross that gulf to Andromeda. And look, even if we could magically travel at the speed of light, the absolute cosmic speeds limit, that journey would still take 2.5 million years. So the reality here is pretty stark. With the physics we know today, interstellar travel is just off the table. Unless, what if we didn't have to travel through all that space, but could find a way around it? And this is exactly where the wormhole comes into play. You've probably seen it in movies like Interstellar. It's this incredible, almost magical solution to our massive travel problem. Instead of taking the long, long road across the cosmos, you just pop into a tunnel and come out at your destination. So, how in the world would that even work? The basic idea behind a wormhole is actually surprisingly simple. I want you to imagine that space-time is a giant flat sheet of paper. To get from point A on one side to point B on the other, you'd have to crawl all the way across the surface. But what if you could just fold that piece of paper, bringing point A and point B right next to each other? Then you could just punch a hole straight through, creating a tunnel that's way, way shorter than the original path. That little tunnel, that's a wormhole. And this is where the name actually comes from. The brilliant physicist John Wheeler came up with this exact analogy. A worm doesn't care about crawling all the way around the apple's skin. It just chews its way straight through the middle. It's the perfect way to picture this cosmic shortcut. But here's the thing. This isn't just some clever analogy or a cool idea for movies. The possibility of wormholes comes directly from the bedrock of modern physics. And for that, we have to talk about the man who started it all, Albert Einstein. So back in 1915, Einstein completely changed our understanding of the universe with his general theory of relativity. And it's all wrapped up in these super complex field equations. Now, you don't need to be a math genius here, but the core idea is absolutely revolutionary. Massive things, like planets and stars, don't just sit in space. They actually bend and curve the very fabric of space-time around them. And that curve is what we feel as gravity. Now, this is where it gets really interesting. Remember in school when a math problem could sometimes have 2 different but equally correct answers? Well, think of Einstein's equations like that, but on a cosmic, mind-blowing scale. They also have multiple possible solutions. One solution, found way back in 1916, predicted the existence of black holes. But then, another solution, found by Einstein and his buddy Nathan Rosen in 1935, describes something totally different, a theoretical tunnel. A bridge connecting 2 different points in space-time. They called it an Einstein-Rosen bridge. We just call it a wormhole. So if the math actually allows for these things to exist, what's the next logical step? I mean, if these cosmic tunnels are theoretically possible, what would it actually take to create one? Let's go back to our paper analogy. To bend space-time that dramatically, to literally fold the universe, you would need an absolutely unimaginable gravitational pull. So what in the universe has that kind of raw power? Yup, a black hole. According to the theory, only a black hole has enough gravitational muscle to rip open an entrance to one of these tunnels. It would be the ultimate cosmic doorway. Okay, but this brings up a huge and kind of terrifying problem. A black hole, as we all know, is a one-way street. Once you cross its event horizon, there is no coming back. So if you have a black hole at the entrance and another one at the exit, well, that's not a tunnel, that's a trap. You'd need an exit that does the complete opposite of a black hole. And that leads us to this bizarre concept, the white hole. It's another mind-bending solution from Einstein's equations, and it's pretty much the perfect opposite of a black hole. While a black hole sucks everything in,
A white hole violently spits everything out. It's like a cosmic fountain, a one-way exit door from somewhere.
This little comparison really lays it all out. A black hole pulls everything in. A white hole pushes everything out. You can't escape a black hole, you can't even get into a white hole. One is a point of no return, the other is a boundary of no admission. So, to have a real working tunnel, you'd need the perfect pair. A black hole for the front door and a white hole for the back door.
Okay, we have black holes. We've literally taken pictures of them now. And then we have these theoretical white holes. But how much of this is real science? And how much is just really elegant math on a blackboard? Let's take a look at the evidence.
Right now, the existence of white holes is a really hot debate in physics. On one hand, a huge argument against them is that they seem to break a fundamental law of the universe, the idea that things always get more disorderly, not less. A white hole would be like watching an egg unscramble itself. It just doesn't feel right. But on the other hand, you have people like Stephen Hawking, who argue that all the information a black hole swallows has to get out somehow, and a white hole is one way it could happen. There's even this super weird gamma ray burst back in 2006 that had some very strange features, and a few scientists have wondered if maybe, just maybe, that was a white hole going off. The point is, the hunt for these things is very much alive. It started as a pure theory in 1935, and it's still being debated and explored today. And then, in 2015, something truly amazing happened. Scientists in a lab actually created a magnetic wormhole. Now, it couldn't transport matter or anything like that, but it successfully tunneled a magnetic field from one point to another. It proved the geometric principle. The shortcut can work in the real world, even if it wasn't with gravity. At least, not yet. So, real gravitational wormholes are still firmly in the theory column for now. But what's so fascinating is that the very same equations that predict wormholes also hint at other, equally wild ways to bend the rules of space travel. And that brings us to something like the Alcubierre drive. You probably know it by its more famous name, a warp drive. The idea here is you're not actually breaking the speed of light. Instead, you're warping space around your ship. You'd squish space-time in front of you and expand it behind you. Your ship just sits there, inside a little bubble of normal space, while the bubble itself zips across the cosmos. It's another crazy but mathematically plausible idea that comes straight from Einstein's playbook. So what's the real takeaway here? I think it's that the universe is just so much stranger and so much more flexible than we can even begin to imagine. Whether our future is in jumping through wormholes, surfing on warp bubbles, or discovering something else we haven't even dreamed of yet, Einstein's work opened a door. He showed us that what seems impossible might just be waiting for us to find the right solution. The only real question left is, which one will we find first?